Proteus, and this 8051. So we'll be working on this, but now we'll introduce the computation inside the 8051. So today mostly I will make a brief on what we are going to work with and what knowledge or understanding we require, and then next day onwards you will be starting the work. So tentatively we can fix a date that say lab sessions, how many lab sessions can be utilized for different tasks. I think you can see from here. So we have saved the task, and this is given the class material folder. So the first part is mostly your recapitulations of whatever you have learned earlier in the theory class, the simulations with interfacing, and particularly will be utilizing the interface of ADC and DAC, which is already demonstrated during that class. So you can easily code that and test it. So task 1 I think should take only one session or so, and you can do, because you are in the home, so you can do it by yourself at any time whenever you are free. And within the task 0, so we have few things to learn, and particularly to learn the filter design and analysis toolbox of MATLAB. Okay, so before we go into that, we should at least have a brief understanding on that how we can go for filter designing by pen and paper. Means if I want to do it by myself, how we can do that one. Okay, and then if we go with this FDA tool, that will actually accelerate our to get the filter coefficients. Okay, but what kind of specifications we need to provide and why those are required? So for that we need to have a brief understanding. Okay, and the material which will be following, mostly the book by Prokis and Manolakis, the digital signal processing. So everything is there, you have to learn it. So hopefully you already have some experience with DSP, and so this book may be useful for that too. Okay, so our target is to finally end up with designing a low pass filter of structure second order, and design a low pass filter with FIR structure and IIR structure. And we'll highlight here today that what are the issues we need to handle there. Okay, so everything is well instructed, you need to follow the instructions and execute. The task 6 actually I do not know where, means if you are coming by within the semester end, then you can execute it here in the lab, or if you are interested by your own interest, you can also realize it on hardware, because the component price is not very high, and so it is up to you, so you can do. Otherwise you can come whenever you are coming, you can work in the lab with this hardware. But up to task 5 we can do it on the simulation, and so you can do it in your home. Okay, so let us start the discussions on the digital filter design and implementation. Okay, so why we are interested to implement a digital filter? Okay, so that should be realized. Otherwise, if you do not feel that this is important, you want to any work on this. So nowadays there is a booming word. It's called IoT, Internet of Things. And what is IoT? It is made of nodes, which are basically electronic circuits or sensors connected to it, and network of those nodes. And those are connected to clouds, and you can do anything you want, like monitoring or user interfacing. But whenever you come to the node end, this is one of the examples. You can find many others. So node end, you will find that there are a lot of sensors. And earlier days, we used to tell this term as sensor networks. Okay. So those sensors should be connected to ADC, and then we can do some filtering here, because these data are not always very faithful in nature, and so you need some means it will be corrupted with noise, and so you need some denoising technique. Okay. And now, since your data, once you use your ADC, it is converted to digital signal, and there are lots of advantages of digital signal that you have learned. So we work with the digital signals, and so inside the digital platform we can develop some filters so that we can get a faithful representation of the signals. Okay. And then depending upon our requirement, like here these sensors are only transmitting the data, and the computations can be done here in the cloud, which is nothing but the server, the computer server. Okay. And then that can be sent to another node, which is basically actuating node, not the sensor node. And then you can again apply some filtering because of this channel communication, so there might be some corruptions in the channel also, and so you need some filter here, and then you can generate the actuating signal through the DAC if your signal, actuating signal, is to be analog in nature. Okay. Apart from that, you can find, say, you are taking some images in a camera, through a camera which is very noisy in nature, and so you can apply a filter. So these are digital signals, and you can apply a filter and you can get a clean image out of that. Now, what happens in frequency domain, if you see this frequency domain structure, so you will see lot of frequencies are available when the picture is noisy, and then when you apply a filter, this is basically a thresholding operation in the frequency axis, and so it keeps some of the frequencies and removes the other frequencies which are thought to be a noise, the contributing noise. Okay. So what we can imagine here, that in frequency domain we can take a window of 1 up to this omega c, and then 0 beyond this omega c, and so that is actually the frequency response of the filter. And so if I multiply these two, the terms beyond the omega c, that will be 0, and the below the omega c, those frequencies will be as it is. Okay. Now what is this frequencies? Very often we call this term as a frequencies, but by that we always mean to say sinusoidal frequencies. Okay. But it is not actually the mandatory that we should always say this to be a sinusoid. It can be a square wave also, and that can also have frequency of oscillations, and that can also be taken as a basis, or the unit vectors, unit functions, you can say. Okay, basis functions we call it. So that way we can do. So this is not mandatory, but at the same time, for the convenience and for the conventional thinking, we should always we will be always specifying the sinusoidal frequencies here. So that means, say for example, we have some 50 hertz, then 100 hertz, then 200 hertz, like that, all these frequencies. Okay. So what my point is here, that whenever we are going to test the filter frequency, sorry, this filter response, the frequency response, what we need to do, that we need to pass a signal of a particular frequency, say 50 hertz, and we need to check at the end of the filter the output, that whether it is 50 hertz or not, if it is within the omega c. So if 50 hertz is within omega c, then the means the signal should be as it is at the output of the filter. But if the signal, say omega c is 300 hertz, and if we are injecting a signal of say 600 hertz, so that signal should be attenuated with means drastically, and it can be closer to zero, the amplitude. Okay, so the basics working pattern approach for testing the filter is to apply a single frequency, single tone frequency, and then see the response, whether it is the amplitude is remains as it is, or it is getting attenuated. Okay, so we learned, which you have already learned in DSP course also, that filter is multiplication in frequency domain, and so the corresponding operation in time domain is the convolution. And whenever we are going to implement this in a digital processor, so we'll be following this expression, hk into xn minus k. Now you can see, notice this expression, the k is minus infinity to infinity, which is very impossible in if we are going to work with the finite domain or our real world. And there are another term which we will see here, that if we are taking k as minus, okay, negative value, then you can see this n minus k term is coming to be xn plus some positive value, right? And which means that we need to have a future samples, which is also not possible when we are working on the streaming data or the real-time operations. So therefore, we need to change these limits to certain point, means certain, within certain finite values. So we'll see that one. And so, as you have already seen that how these digital signals are represented. Okay, so first is we got to discrete time and discrete value signal. So for that we sample. So this is discretizations in the time domain, and then discretization in the value or magnitude. Okay, so set of points in these discrete points and set of discrete points in this. And so whenever we are trying to specify the digital signal, so the functional value belongs to z, so this means the integer one. Okay, so integer set of integers, and so the time is also set of integers n, but it is implied. So this one means 1 into ts. Okay, so this one means the ts, so the actual timing is ts, then 2 ts, okay, then 3 ts. But when we specify, so this ts term is not explicitly represented, but we only take this 1 2 3 and all. So okay, so now ts is one factor which will also come in the representation of the signal, and we need to be concerned about that, because of this sampling we have some issues which is to be taken care. And so for discrete values, which is quantization, and quantization is done like this, say fn equal to fnts, and so this is the floating or ceiling or round off depending upon your quantization process. Now the circuit element, what we have already known, that analog to digital converter for that. Now, what happens when we digitize a signal? What happens to the frequency line? Okay, so as per sampling theorem, so which is proposed by say Shannon, and there is a rate called Nyquist rate, which is telling that this maximum frequency component so should be less than equal to fs by 2. Okay, so fs is the sampling frequency, and then so what happens, the analog frequency range, the valid range, becomes fs by 2 to minus fs by 2. But why we call this as a valid range? Okay, how does this Shannon sampling theorem came into picture? So why we are concerned, or why always telling that it should be fs by 2? Okay, any idea from students? Anyone? I want a response.
Sir, generally the analog signals are of sinusoidal type. They have a positive cycle and a negative cycle. So for positive cycle there must be one sampling, and for negative cycle there must be one sampling.
No, no,
So
no.
to
Uh, First is that these minus negative frequencies is for mathematical convenience. So there is no physical significance for that. If we want to assign a physical significance, we can do with a phasor rotations. Okay. Otherwise, we do not have any physical significance to it. But the main constraint is because of say as I said that we need to reconstruct the signal at the DAC end. Okay, so you have also seen during the demonstration of ADC DAC interfacing in your theoretical class that you have seen that we reconstructed the signal back into analog domain, right? And so during that means if we need the reconstruction of the signal, then only the Shannon sampling theorem is applicable, and we tell that the frequency limit should be fs by 2. If we do not need any reconstruction, we only want some informations extracted from the samples. So then this Shannon sampling theorem may not be utilized there. Okay, and we can do some tricks also, which nowadays is called compress sensing. So with that, we can reduce the frequency of sampling further. Okay, but whenever there is a requirement of reconstruction of the signal, these limits are to be followed. Okay, so now you imagine that there is one frequency within that band, and then whenever it is we come into digital domain, we define the frequency with small f, denote this it, and we call digital frequency. Now digital frequency is f by fs, and this will always be within the half, minus half to plus half. Okay, so this is in means for the Hertz component, and for the radian component we will be having correspondingly this is minus pi to pi. Okay, so this will define our frequency range in terms of minus pi to pi or minus half to half whenever we are talking in digital domain. But it implies that this is basically this minus half is corresponding to fs by 2 or the twice pi fs by 2, right? So this twice pi fs by 2 is the omega. Okay, so omega range will be twice pi fs by 2, and which is coming to be pi fs, and therefore with our relations between analog and digital frequency, we get that this should be pi. Okay, so it is always happening, but it is implied that it is means we need to know the sampling frequency to convert this signal back into the analog domain, right? So we found the limits of the maximum upper frequency range is fs by 2, that is theoretically, but in practice we'll take it fs by 10, so that in one period of sinusoid we get at least 10. So this is very easy. Why do we need to do that? Because if that will actually increase the density of the samples, and so our interpolation between samples will be better than this. So if we take further, so that means this fs should be this greater than some mfm, okay, some term. Now I said in practice we'll take this as a 10, we can take it more also, okay, so greater than 10. But we need to compute more samples or utilize more samples. Now what happens when we go from analog domain to digital domain? What happens to the frequency rate, frequency components? So if you see that in analog domain, if there is signal like this and the corresponding frequency range is from -b to b and shaped is like this, then what happens when we digitize this signal with certain sampling frequency? So that sampling period is t, so sampling frequency is 1 by t. We'll get the replica of these analog frequency response, means frequency representation, means around 0, fs, 2fs, and like that. So what is the implications of this? That what we need, that these particular band we need to select. So for that what we require, that we require a anti-aliasing filter prior to the ADC. Now whenever we are applying anti-aliasing filter prior to the ADC, this means that we need to have an analog filter. Okay, how can we employ an analog filter? So there are several ways. One is say only using the capacitor, inductor, or resistor, so passive elements. Another option is using the active elements, the op amps. Okay. So with that, what we do actually, we eliminate these frequency components and we keep only this one. Okay. And so that, so what it means that by using the anti-aliasing filter, we are making our signal band limited. And if you see in Shannon's sampling theorem, this is one of the key terms, that the signal, input signal, must be band limited. If it is not, then decisions on the sampling frequency would be difficult. All right. Now, how to decide that band limitation, the band? For example, that our speech signal, the voice. Okay, so whatever we speak, so that has maximum 4 kilohertz of the band. So 0 to 4 kilohertz band is fixed for that. So beyond that, those are not meaningful or means for any informations. So what we can do, we can at least use a 8 kilohertz frequency to sample that one. All right. And so what we can do, we can take one speech signal and then employ a anti-aliasing filter, which is essentially low pass filter. Okay, and then the output of that low pass filter is fed to the ADC. Okay, so this is analog in nature, and this has some FC, the cutoff frequency, and as I said, depending upon the signal, we can do some experiment on that, and say we are using the speed signal, and so it has maximum 4 kilohertz. So we place this cutoff frequency as 4 kilohertz, and then at this end we'll get a band of frequencies up to 4 kilohertz, and so it is easy for us to decide the sampling frequency fs as greater than equal to 8 kilohertz. Now what you can do, you can find your microphone and you can do this experiment with MATLAB also. You can record this voice and then you read that speech in the MATLAB. There is audio read or wave read kind of functions are available there. And in the information, just if you just see that information instruction is also there, or it is the point means class structure. So from there you can get the sampling frequency and see what those sampling frequency values. So you may see that it is a 22 point something, sometime it is 48 kilohertz. Okay, sometimes it is 11 point some kilohertz. So you see those frequencies, so whether they are maintaining the Shannon sampling frequency theorem or not, or Nyquist theorem. Okay, so this is one example. Another example, when you are using digital oscilloscope. Okay, so there also you need to have this low pass filter analog and then connected to ADC, and then it will go to the, through this processor it will go to the display. Okay, so what we can do here, that we apply a signal, we use a low pass frequency means filter with a cutoff. Now this cutoff is defined in terms of minus 3 dB. Okay, now how this minus 3 dB is coming in? Anyone from the student?
So minus 3 dB means the power will be half.
Yes, very good. Okay, so below that power, we don't consider that the signal is valid signal. Okay, so we then apply this ADC with sampling frequency Fs. So now Fs would be at least 2 into F max, this frequency. Okay, so this we need to have, right? And then this, the ADC will convert it into a digital value depending upon the number of bits it uses to represent this data. Now we are in the digital domain, and so what we want that, so the signal actually based on, in our case we'll be taking a single tone, that means single frequency, so the sampling frequency can be decided from itself, but in reality this is the scenario. Okay, so we'll apply an anti-aliasing filter, but in our case we may not need this. Why we do not need? Because we will be applying one or two frequencies or so, single tone basically, so we do not need this, but in reality we need it. So after we get this ADC output, the XN, so what we can do, we can employ this uh, operation which is called the convolution. Okay, so this HK, then X n minus K, and now because we are working in finite domain, So let us vary this k from say 0 to some m minus 1. Now this m, if you take it say 2, then it will vary from 0 to 1. So if you take it say 3, then it will vary 0, 1, 2. So you can see that this is x n minus 1, okay, this is x n minus 2, this is x n minus 3, and like that. So we are only considering these three delays, the three past samples and the current sample, and then we can multiply with certain factor which is coming from this hk. So hk is basically this a k, okay. So we multiply, so we need a multiplier or multiplication operation, and for that you already know in case of 8051 we have the function called mul_ab, okay. And say this mul_ab takes a number of clock cycle and or say total time of execution is tm, and then we have to add these components. So we have corresponding instruction, say add or add c and some register say b, and this takes say ta, right. So what we can think of, that we have consumed some time here, this t, we have consumed for all these multiplier the t component, and then we have this ta. Now if we have a number of multipliers inside the processor, which is not in case of 8051, okay. So if we had the number of multipliers or number of adders inside this processor, then our computational complexity, which means that giving the signal xn, and then when we are getting the signal, the output signal for that, so we'll get this tm plus ta plus ta plus ta. So this tm plus 3ta would be the timing, because we can assume that if we have this all the required multiplier available with us, then these multiplications can be done in parallel, and so it will only consume tm. But these additions, since they are dependent on these all these earlier adders, so these additions are required. So tm plus 3ta would be the means after that the we'll get the output, and after that we can get the next sample, okay, and this sample will move to this direction. But since in 8051 we do not have such a situation, that means we do not have number of multipliers or adder. Instead, we have a single ALU, one ALU. So all these computations should be done through this ALU, and therefore we have to add all these timing. So in this case, say 1, 2, 3, 4. So 4 Tm plus 3Ta. Okay, so it will take at least 4Tm plus 3Ta, and after that you can go for next sample. So this will decide the sampling frequency of your system when you are employing a filter inside the processor. Now what are these factors? These 4, these 3, that is related to this order of this filter. And so if you increase the order of the filter, obviously this time will increase, and so your sampling frequency will decrease. And then what you have to do, we have to actually say in reverse way that if we employ say m equal to 4, so fourth order, or so what we can say, that we have 0, then 1, then 2, and then 3. So say third order, m equal to 3. Okay. Uh, yeah. Yeah. So, or sorry, this m equal to 3 means 0, 1, 2, right? So xn in my notation, it will be xn minus 1 and xn minus 2. Okay. So if that is the case, so then this 3 will come here. So, or if you take it 4, then the xn minus 3 is also included. And so what is needed? We need to have, so in general we can tell this is m equal to m into 3 Tm. This m is for multiplication, plus m minus 1 into 3 Ta. So this would be the time which is required to compute it. And then the sampling frequency or sampling period would be this one. So this is our sampling period, Ts. And so sampling frequency would be 1 by Ts. And so we'll say that it can only so from this relation we can say about this maximum frequency that can be valid for this particular system. So what it means? It means that say we found from here it is 3 kilohertz. So we'll say that my implementation or my system, this system can only work for the frequency up to 1500 hertz. Okay, so just 3000 by 2. So that is the valid range for this particular implementation. So that way we can say, okay. And then if we find that some of the signals are having a maximum frequency range up to 1.5 kilohertz, then we'll say that my system will work there, right? So the implementation structure or the algorithm that decides what will be my the signal input signal frequency range. Is there any question? Or you have understood this?
Understood, sir.
Okay. So in this digital framework, filtered framework, we have some technical issues. So we need to think of one is the digital filter design, how we can get this these coefficients A0, A1, A2, A3. So that is the aim of this filter design process, and we'll see some example of that. And then we need to have implementation. So this implementation should be able to reproduce magnitudes accurately, so which related to computational accuracy. Okay, so the representations of data, so related to that. Then it should produce a finite output for a finite input signal, so which means the stability, and very often you have learned it as a Bibo stability. For bounded input it should have bounded output, and so we need to find whether our implementation is stable or not. Now, in case of analog systems, the op-amp and every means other circuits, we have easily applied the theory from control system, right? So, how this is applied in digital systems also, whether it is required or not, this is definitely required. And what are the source of instability? So one of the sources in digital case is the precision of the sample representation. Okay. So as I said that the data which is represented by ADC. So ADC output is, say for example, for ADC 0808, it has 8 lines with us. Okay. So it means that it divides the whole range of the signal with 256 levels, right? And so we can have a minimum resolution of the signal below which we cannot get that signal value. Now in that situation, if means very often we have to truncate, means quantize. So the ADC is also not only quantizing the time axis but also quantizing the value or magnitude axis, right? And so depending upon that, we can have, say for example, I have 5.23 one value, another value is 5.232. Okay, but when we use a rounding off technique to round it off up to say second decimal places, so what we find, they are same. Now if that happens for say a poles of this of your implementation, the filter, okay, so what will or so then what will happen, that two poles which was actually separated from each other, and because of that you get certain frequency response. Now because of this imprecision in the data representation, these two poles appear to be same location, and therefore the frequency response will change, right? And so our system which we thought to be implemented with different poles, it actually got implemented with same poles or poles at same locations, right? So and that may affect the stability of the system. That means if I give the bounded input or finite input, I may not get the finite output, right? So we need to think of that. Then reproduce the signal of frequencies within the cutoff frequency, which is basically related to the timing, because it depends, it actually decides the sampling frequency, and then within that sampling frequency, half of the sampling frequency, that FC should be there. Okay, so that value should be there. So now with this, let us see this, as I said earlier, that with the original expressions of convolutions, we actually need to have this future value of the signal, which is not possible in case of streaming data. And therefore what can be done, we can put certain constraint now in our system. and that we call it as a causal system. All of you have learned this in various subjects, control or the DSP or so, that causal signals. You learn the definitions. Now you have to apply it, that this causal signal is for which this Hn should be 0. So if this Hn is 0, then we can easily cut down this component, and then we can take this one 0 to infinity. All right, we have another infinity here, so we can come to this. So we need to implement, we are going to implement a causal filter, causal digital filter, and then this filter operation is nothing but convolution, which is a linear operation, and so, and that also you have learned, a linear system. What is a linear system? Response from the student. Yes, anyone? What is a linear system? What is time invariant system? Anyone from the student? I want a response.
Linear system is a system in which superposition theorem can be applied.
Yeah, with zero initial condition. Okay.
Yes.
So the graph would pass through the origin. Okay. So this is one. What is time invariant? Time invariant is if I give a delayed version of the input, with the same amount of delay, the output will also be shifted. Okay. So that we are going to implement, and then the ideal filter characteristics. So now we are in the digital frequency domain. So this small omega is digital frequency in radian, and as I said, it will vary from minus pi to pi or 0 to 2 pi. So I can just have a shift on this. All right. And then we are finding the amplitude. So this is 1, say this magnitude is 1, and beyond this cutoff frequency, so that means omega c to pi. Okay, so that will be 0. Now in analog frequency, what is the corresponding value? So this is your fs by 2. Now depending upon this analog frequency range will vary. Okay. So if it is 3000, it will be 1.5k. If it is 100, it will be 50, and like that. But in digital domain, this minus pi to pi will not change. It will always remain constant. So our function means this characteristics, ideal characteristics is 1 within omega c and 0 beyond omega c. So now this is the in frequency domain. If I just take this and invert this, so we'll be using inverse Fourier transform. We'll get the Hn. And what is Hn? Hn is the impulse response of the system, right? So that impulse response would be omega c by pi at n equal to 0, and then remaining other omega c by pi into sinc function, the sine omega cn by omega cn. But you can see this is non-causal, so we have some non-zero value, means below this n equal to 0 for n negative. So what we can think of, so that was the ideal characteristics of the filter, and it is a non-causal filter. So from this we can say that we cannot implement the ideal filter characteristics. Then what is the practical filter characteristics? So this has actually been proved by Paley-Wiener theorem. So which is telling that for ideal case, this particular integral should be finite, and if I apply this, then we can say that this amplitude, this h omega mod cannot be zero throughout a band of frequencies, but a finite number of points we can have this one, and that's why you can see that the implication of that statement is that we cannot have a constant one here, but a wavy kind of thing, so which will vary within this band, right? And same thing will happen for this zone. So we cannot have a constant values of 0 here, but we can have a small oscillations depending upon the attenuation factor. Okay, so it means that for this particular frequency the amplitude will be 0, but for this particular frequency the amplitude will won't be 0 but closer to 0, right? So the key observations for practical filter characteristics is that frequency response h omega cannot be 0 except at finite set of points in the frequency. So we'll observe some oscillations in the pass band as well as in the stop band. And then with the magnitude cannot be constant at any finite band of frequency. So we cannot get a flat response that the ideal filter possesses. The transition from the pass band to stop band cannot be infinitely sharp. So that is the very basic reason for that is the inertia of the system. Okay. So we cannot do, and because of that we'll have some oscillations also. Then the real and imaginary parts of h omega are interdependent, and therefore this amplitude and the phase cannot be set arbitrarily. Okay, so whatever I am summarizing here, all these are available in the book by Prokis and Manolakis. So if you want that why these statements are given, so you need to go through that book. Okay, in the filter design sections. So now the general filter is of this model. That means we have some included some pass value of outputs also, and then we can have the hz, so which is a z transform of that, and hopefully you all know what is z transform, and you also know that while you are speaking about any Z transform, you need to specify the ROC of these. Okay, and ROC would be for which this denominator term is not equal to 0. Okay, and then what we can do, that these poles and zeros, so that should be, so that if it is, you know, this covers this unit circle, then we can do that. So it cannot be done in general, but in particular this unit circle should be included by, or covered by this ROC. Okay, so that means if I say, and then I find that the Z is, so this is 1, and then I find that the ROC, so this is our ROC. Okay, I'll take this one, and then this is unit circle. So if the unit circle falls within the ROC, then only this is possible, this conversion from Z domain to Fourier domain, otherwise not. Okay, so we assume here that this is true, and so this Fourier or frequency response is available to us. So in filter design problem, the aim is to approximate the ideal frequency response by frequency response of the LTI system. This is this model, and with proper choice of AK and BK. So out of that general model, we can see that if we only take the past values of inputs, we call this structure as a finite impulse response. Okay. And finite impulse response, because this impulse response, so the convolution expressions from there we get, this is related to impulse response, these coefficients. Okay, and which are having 0 to m minus 1, and so it is having a finite non-zero values, and so we call it as a finite impulse response, right? And so this bk equal to hk for all these 0 1 to m minus 1. And in frequency domain, if we convert this, we'll get sum of these hk into z to the power minus k. So zeros of the filter can be found from the roots, and the desired characteristics very often we employ in case of a FIR filter structure is the linear phase. Now, why linear phase is desirable? Okay, so you see that if our original impulse response or the frequency response is h omega equal to 1 to 0, and within this band, and if we multiply it with say e to the power minus j omega n 0, which is basically giving the linear phase. So if we see the phase versus omega, so we'll get a linear response with slope as n0. Okay, and so what happens in the time domain, so you will get that this hn is only shifted, the shape of the signal remains as it is, but only shifted in the time. So it means actually that all these frequency component will have a same amount of delay. All the frequency component of the input signal will have a same amount of delay, and it will produce a delay at the output end. Okay, and this is also called, can be called as a group delay. So all the components are having similar delay. Okay, and that's how that the actual shape of the output for a particular input will always remain constant. Okay, which is very often we desire, because say for example that the shape is changed. What does it mean? It means that the frequency amplitude of the frequency components are different for different frequencies. Now if it is happening with the speech signal will be completely distorted. Okay, so to avoid those distortion our system should be able to employ a linear phase, and that linear phase, actually if we employ that linear phase, it basically means the pole zero representation of it we will have, that that actually gives us some advantage. And this is hz and hz inverse, they are having identical roots. Identical roots means like this. So this z1 z2 z3, they are from the hz, while that z inverse, so they are from the hz. So these are across the unit circle. This is symmetric in nature, and that's why we call that is a symmetric filter. And the time domain expressions will be this hn equal to plus minus h m minus 1 minus n. So now let us fix this m, say 4. So what does this mean? So it will vary from 0. So this n will vary from 0 1 2 3. right? And so the h of n, so h of 0, so h of 0 will be equal to m minus 1, so 3 minus 0, and so this will be h of 3. Then h of 1 will be equal to h of 2, right? Now from this we can gain out of this information, right? So while we are trying to implement this filter, this one, so we need to store these coefficients. Now since we find that these pairs H0, H3 and H1, H2 are same, so instead of consuming 4 registers in our RAM, okay, we'll only consume 2 registers with the value of H0 and H1. And then while we are multiplying, we'll take care of this H3 and H2 component. So if our filter, FIR filter, is a linear phase filter, then it can have a symmetry with Hn equal to plus Hm minus 1 minus n, or antisymmetric Hn equal to minus H of m minus 1 minus n. But so in means what we can do, we can have negative value of that or positive value. So but at the end we are having a reduction in the memory usage, so that is a better options for us also, right? So this linear phase gives us some advantages, and if we summarize that the what will happen for different conditions of m, that means if it is an even or if it is an odd function, so we can have a symmetric, that means hn equal to plus hm minus 1 minus n, or antisymmetric, that means hn equal to minus hm minus 1 minus n. Okay, then if we see the magnitude of the real component of hr, magnitude of the real component of hr for odd and even case of m, we'll find these expressions. Okay, so I will suggest you that to derive all these expressions by yourself, at least which are available in the book, but you do it on pen and paper to just embed these things in your mind. Okay, and then phase will be like this, and you can see these are all linear with respect to the frequency. Okay, and then what we can find, that we'll just place a 0 frequency. Okay, so if I place a 0 frequency, I get this magnitude of hr for symmetric component with even filter becomes, you know, uh, this value, right? So which can be any finite value. Then for this odd, this is okay, for this is hm minus by 2 for pi. Okay, now what we are finding, that for pi, which is basically at the higher frequency end, so this value becomes 0. And similarly we can observe that for anti-symmetric cases, for say 0 frequency, that means low, so we are dividing the frequency band into low and high, and we are finding that in the higher frequency band, what is the response of this magnitude of this filter, and we find these are zeros. Okay, so this yellow shaded one is the zeros, all are zeros. Then what it means, it means that we cannot implement a high pass filter with the symmetric and even filter order. Okay, similarly we cannot implement a low pass filter with antisymmetric and even filter order. And same thing is true for odd filter order with antisymmetric. For now, this is actually true that we cannot employ the low pass or high pass filter with these antisymmetric component with odd filter order. So this is completely cannot be implemented. Okay. So now we are coming to a point that we learned that this antisymmetric case or symmetric case will whether it can be implemented or not for different order of filters. So then our choice when in this software environment it asks for the number of the filter order. Okay, then we can use this information and provide the correct value of the m, the order of the filter. Okay, depending upon our requirement. Now we want to determine and we'll be working for first the FIR filter design. And one popular method is called window method, and which is also easy to conceive. So to determine the coefficient Hn from the specification of desired frequency response Hd, right? So Hd is given to us and we need to find this Hn. So how can we do that one? So HDN can be just inverse Fourier transform of this given frequency response. Then in the time domain, we'll use a window, and in this case, we'll call this window as a rectangular window, which means that it will truncate this HDN after certain time, okay, or beyond certain time zone. So as we have seen that the original or given frequency response may be non-causal, and so by multiplying this window we are making it causal. So we are only taking finite number of samples of these frequent impulse response. Okay, and so the unit impulse response Hn would be the HDN into this Wn or omega n. Okay, and so this is a multiplication operation in time domain, and we know that this operation would be converted into frequency domain as the convolution operation, and so we can get this frequency response by employing the this frequency response, the desired frequency response convolved with the window frequency response. Okay, so what we can find from here, that window frequency response, we can find the expressions easily by applying the Fourier transform of it. We can get this is a sinc function with certain delay, and that delay would be our phase of that, means it will affect the phase of the system. So amplitude is this one, and then this theta phase is minus omega m minus 1 by 2, and this plus depending upon the value of this positive or negative. Okay, so we can plot it easily, and what we can find that if we are increasing the order of the filter, the main lobe is getting reduced, which is very often our requirement. And to reduce these, so this is with m equal to 31, then main lobe is further, so this is means it is selecting more number of frequencies compared to the m equal to 61, which is selecting less. So that means it is its quality factor would be better than the others. But at the same time, if we increase this m, so as you have seen the time, so m into tm, Okay, so that will also increase, and so this will reduce the band of our of interest. Okay, so we need to have an optimum choice of that. And so what we can do for symmetric filter, this would be our HD. Okay, and the HN corresponding to that would be this one. So we have multiplied the window here, and then if we find the HW, so just Fourier transform of this HN we can do. So we have developed this graph, computed this graph from this information. Fs is 3000 and cutoff frequency is 300. Now you notice I have taken a factor of 10 between these, and then m as 101. Okay, so what we observe here, that we have main lobe 0 to 300 across, means around this point. So we have this minus 3 dB. Okay, and then the side lobes are very less below, means it starts from minus 50 and going next one, means lower side. Now if we so what we have done earlier, we have taken the rectangular window, we have just truncated, but what happens due to this truncation, that the continuity at the frequency n, or this in the time sample, that is lost, and because of that we get the side lobe components which are non-zero. Okay, as well as it might be of oscillations, that means this might be of significant values in some cases. So we can have different window, like one of the window is Hamming window, and we this with the shape 0.054 minus 0.46 cos of this, and this is completely empirically derived by the different persons or people. And so now if we employ that one, we'll see that the this response has little bit changes. It is almost wavy less, but if you actually zoom this area, you will find that it is not exactly constant. It is in wavy in shape. Again, we can find that here our 300 hertz are available. Now, if we means plot these two cases in same plot, so you can see that this rectangular window, the side lobe energy is attenuated less compared to the Hamming window. Okay, so that means that window, the selection of window definitely have a role of the for the frequency response. And so what does this means, that this is less attenuated? It means that some of the energy from these frequency components will also contribute to the energy of the output signal, right? Which we do not want, because any frequency, say here, should have only its energy, but when you see the output, if there is not significant reduction in the side lobes, so those frequency energy will appear in this desired frequency amplitude. Okay, so that amplitude will be different than what you are supposed to get, right? So that will affect this energy and the amplitude. So there are number of windows, say von Neumann windows, Hamming windows with different expressions. So what you have to do, you have to just multiply those windows with these expressions, and you can get this output. Okay. Then Blackman, then Kaiser, and then all of them, like Kaiser, they have some tuning parameter. That means you can vary those parameters and check the response and select a particular response which you want that it should be depending upon your application requirement. Okay. So in visually, this is rectangular, von Hand, then Kaiser with WA as this. So there are obviously effect on this choice of these. So Kaiser is much, so you can see that if we choose 1/8, you are having a discontinuity at this with certain magnitude. But when you are going with different values, this discontinuity is changing, right? So WA equal to 1, almost continuous one, and very often we require this one. Okay. So in case of FIR filter design, we can employ a window method, and depending upon the application and the frequency response requirement, we can choose a particular window, and if there is some tuning parameter, we can choose those tuning parameter and see the effect in the frequency response. Okay. And what else? The sampling frequency, the cutoff frequency, and the order of the filter. So all these are means requirement for filter design. Okay. Now, while we go for designing an IIR filter, so IIR means the infinite impulse response. We actually include the past values of the output too. So that means we can vary this k from 1 to m minus 1 or so, and we use this ak y n minus k, and then we add, so this will be subtracted. So that is the general model we have shown earlier. Okay. And then we have this k equal to 0 to m minus 1. Okay, so this m can be different also. So this may not necessarily the same number of poles will be there. So you can say this is up to n. And so bk x n minus k. Okay. And so what we want to find this ak and bk for a given frequency response or so. Okay. Now for FIR filter we had used that approach. For an IIR filter, so since this ynk, the past values of ynk is included, so at a particular time instance we have all the past values and the in past input values and the past output values. So in effect we are not truncating the impulse response. So since the minus infinity term, if your system is running for continuously, means for long hours, so it is as if it is taking from the minus infinity to plus infinity, as if. Okay. And so that's why the impulse response is not effectively getting truncated, and so we are taking all the infinite number of samples which is actually encoded in the past values of the output. Okay. And so we call it as an infinite impulse response. And then what we can do for doing designing this one, we get the analog filter transfer function, so that which is generally expressed in the Laplace domain with HS. So what it means that hs is known to us, okay, and from there we'll try to derive that hz, and if that ROC, okay, so that ROC is covering the unit circle, then we can find, I mean, the frequency response will exist, and then we can find the h omega, right? So there are several methods which is called approximations of derivatives, then impulse invariance, the step invariance, direct substitution, the matched Z transform, the bilinear Z transform. So mostly we can use this one. So because this one is having a properties that it will always produce a stable digital filter from a stable analog filter. Okay, so these are very simple one in a sense that we use this differentiation term xt as xn minus 1 by ts, and so the time derivative is equivalent to multiplication by s, and so the s can be said as s equal to 1 minus z inverse by ts. So again s is sigma plus j omega, and therefore we can find z equal to this one. Okay, so we are, what we are doing actually, we are trying to map from Laplace domain to the z domain. Okay, so that's how, but with these approximations. So one example can be thought of that given a sampling frequency 1 kilohertz, we have a filter which is the IIR response filter. Okay, so s square plus 400 s plus this one. So we can just replace this s using this 1 minus z inverse by ts, and we can find the hz. Okay, and once we find the hz, we can easily convert it into this yn equal to past values of output and past values of input, including current one. Okay, so that we can do. So because this is nothing but yz by xz, the input. So we can easily convert, right? So this is hs available in analog frequency. This should be analog frequency, and this is also shown with analog frequency, right? And the valid frequency range is up to 500 hertz. Okay, because the 1 kilohertz is the sampling frequency. Okay, now what you can find that up to 500 hertz the frequency response is similar. Beyond 500 hertz it is just replica of these, and so we can easily see that we can utilize this expression hz to implement an IIR filter, right, of the similar shape, right? We have some reduction in the magnitude, but that can be taken care with a certain factor, multiplying with certain factor, and this is basically, I think, the factor would be related to the ts, the sampling time period. Okay, so that is not very significant. We can just use this ts factor to this, right? So we can employ, so now this example with certain that ts, employing that ts in the expression, we can get this and we can derive these expressions with this, and so we can develop this. So 0.00 this value multiplied, then delete, and so we have these past values of this. Okay, and this can be coded in digital processor. Okay. Then bilinear transformation. So for that, what is done is it is telling that z equal to some e to the power s0 into ts. So if we take this as the mapping, then we'll find that all these right hand side poles or zeros are within the maximum, means whatever is maximum within that. So that will be the radius of this. So whether zero or poles, and then it will converge to within this. But now in this case you can see that this may not be always unit circle. Now for a system, the digital system, to be stable, this should be within, the poles must lie within the unit circle. Okay, so this may not be unit circle. So I should say this may not be unit circle in general. Okay, so based on the value of this ts, we can have this non-unit circle, right? And so what we can do, so z equal to e to the power sts, and we can only keep this one if we do, as I said, that the poles may not always lie within the unit circle. So that means that it may produce unstable digital filter from a stable analog filter. So to avoid this, a tricks is applied. So the same mapping, but with this e to the power sts by 2 by e to the power minus sts by 2, and then we are keeping the first two terms in numerator and denominator. And when we apply this transformation, we call it as a bilinear transformation. Okay, so we find that it produces a stable digital filter from a stable analog filter, right? So you can find with this expression that any value in the left hand plane of this S plane will be within the unit circle. So this is given with, say, ts equal to half unit, and so you can, if you map this, it will always be within the unit circle in the z domain, and therefore we'll get a stable filter out of this. So what we learned so far is the way of filter design for the FIR structure and for the IIR structure. While for FIR structure we start with the desired frequency response, we use a window method, but that is not the only method. There are number of other methods. Okay, so for details you can go through the book, but we choose the window method because it is widely used and it gives a quite easy notions for designing that. And then for IR system, we basically use the analog filter design. So that means with the given specifications, we need to first design the analog filter. So that analog filter is already, means that is a mature domain, and so we can easily design that analog filter. Once we design the analog filter, means we have the HS, the transfer function with us, and then we use the S to Z domain mapping, and there might be several different ways of mapping, and one of the ways is the bilinear transformations, which is giving us a stable realizations of the filter, and that we can use. Okay, now to make our life easy, that there are different software where we can actually get this filter design done. So whatever we learned so far, so that is for to make our background, to provide this information which is required by the software. Okay, and we should be able to put the correct informations into that. So let us see in the FIR. So I think if we can write FDA tool in the command prompt, so it will open another window. Okay, it is telling that in future version that filter designer we have to write instead of FDA tool. Okay, so still it is busy, so it will open, so you have to wait a little bit. So any questions so far? If you have any questions so far, you can just raise.
No, sir.
So I assume you understood.
Yes, sir.
Yeah.
Sir, can you please tell the book's name again?
Digital signal processing. Okay.
Okay, sir.
By Prokis and Manolakis. The author's name.
Thank you, sir.
So I will try to upload, if possible, here the soft copy of it.
Okay, sir.
Okay, so let us go back to this, and afterwards I will come to here if that opens. So at least I think you can see. Okay, I think it has come. Yeah. Okay, still it is initializing. Yeah, so it has come. You can see it easily. Okay, so you can see that there are several options here available. One is that whether you want to design for low pass or high pass, whether you want to go for a FIR, and if you click this FIR structure, you have option called window, and as I said, there are several other options. Okay, so all are targeting to find, means approximate the desired frequency response. And so with window we have options that what kind of window we want. Say we have used this Hamming window. Okay, and then we need to specify the order. Say we are, whatever we have, it means shown you that figure, so that is actually generated using the code, the MATLAB code or the science lab code, but that can also be generated here. We can find it from here. Okay, and so the frequency fs we had taken, say, 3000, and fc we had taken 300. Okay, and so what we have done, mention the filter order, mention the window frequency and the sampling frequency and cutoff frequency, and we want to design it. Okay, so if you click the design filter button, so you will get the frequency response in this window, and we have several other buttons here, from where, like here you can see that. So you can see this one. So what it is showing us, the only positive side of this. Okay, so no negative side is shown to here us, and you can easily see that they are providing this as the frequency response up to 1.5 kilohertz, the fs by 2, right? And so what you want to know the coefficients, the b and a. Now this is an FIR filter, so that means it only takes the past and current value of the input signal, so the we'll get only zeros, right? So if I click here, this b comma a, they are telling, it is telling numerator, and numerator the values are given here. So since the order is 101, so it is giving 101 values. So let our order be say 10. Can you choose 10 for low pass filter? That's what I pointed out, that table, that whether for low pass filter, for symmetric filter, can we do it, or anti-symmetric filter, can we do it? Okay, for M even or M odd. So those each question should be raised in you, right? And so say we are doing a filter order, say second order filter, right? And then we want to design it. So it is giving three values, xn, so 0, h0, h1 and h2. Okay, now what about the frequency response? So let us see it. Now you can see the frequency response is something like that. So what does it mean? So minus 3 dB has not been reached up to here also. Okay, so it means that with second order it is difficult to achieve. So let us see with 10th order. We have some changes in the frequency response. Okay, and so say 300 means zero point 0.1. So okay, up to this, so 0.1 here, so we can expect that this can be. So I think we can zoom this part, and so we have 0.1, 0.1, so it is within minus 2 dB, right? So it has gone up to say here, so let it be, so we can think of say minus 3 dB. So anyway, so it has gone a little bit larger than this 300, but it can be sufficient. Okay, so this 10th order filter or 11th order filter or so we can implement in our 8051 or so, right? So what is your task? Your task is to explore this filter designer and then once that filter is designed, you get the values. That value should be stored. All right. Now one question should be raised here, that you are finding these values are very small, okay, and in fraction. All right then. Now, if this is the case, how to represent these fractional coefficients in 8051 or digital processor, which has finite amount of word length or bus length? So that is one issue we need to take care. Okay. So similarly, you can have this IIR structure, then you can have different options for that. So which we have not covered, we have only covered that this analog domain to Z S domain to Z domain mapping. Okay, so apart from that, there are digital means designing the filter in digital domain itself. So we can have, say, Butterworth filter. Okay, and with that we can specify the filter order, and then we can have this fs again, low pass. And if we go for designing that filter, so we have numerator, we have denominator, and we have again. Okay, now you can see here that it is telling section 1 1 to 1. Okay, now section 2 1 to 1. Okay, or means we have numerator denominator. Section 3 we have denominator numerator. Section 4 and then section 5. So what does it mean? It means that this filter order is divided into second order filters, and since it is a 10, so we get a 5 sections like this. Now what is the reason for that, we'll learn. And so this filter design is giving us a better way of, means directly giving us this second order filter, which is to be cascaded. So we'll let us go back to our presentation. And so what we learned up to this, that we do not need to actually uh, compute the filter coefficients on pen and paper, but we can utilize a software which can be which will provide us those coefficients. And so now one of the issues what we find, that the coefficients are in fraction, and then we need to represent this fraction into the 8051 or any digital processor, which are actually integer, means which provides us an integer computation platform. Okay, so it does not provide us a floating point platform or so. What we need to do, we need to represent the data with a virtual means concept, or virtually we need to represent the data with the decimal points. So what will be means concentrating on here, the range of the signal or the function. So say our signal is varying from 0 to 5 volt, okay, or minus 2.5 to 2.5. So in that case, what we can find, that to represent the 5 volt, we need at least 3 bits, and so 3 bits should be provided to the integer field. Okay, sorry. And then we need to once this integer field is given, okay, and if we know the word length of that, that means, say for example in case of ADC, okay, and that is ADC 0808. So the same thing can be extended for any ADCs which is having 8 bits. So this we are fixing, means which is already fixed, this word length W. Q we find, so we can easily find the QF, the fractional component, fractional field. Okay, so that will be W minus this QI. Okay, now the term I am using integer field, then fractional field, and in between we have the point. Okay, so QI, then QF, and so we denote this structure by Q I dot F format. Okay, now for 5, the 5 volt, we need this QI to be 3 bits. Okay, and since we have 8 bits, so QF would be 8 minus 3, so 5, and so we'll tell this representation as Q 3.5 format. Okay, so very often we need to do, we'll see with example then that how these are coming. Sometimes we have the precision also. Okay, so precision, the QF is defined, so then we can utilize this QF to convert this floating point number to the fixed point number, and then we try to find the integer or the word length if it is not fixed. Then we have precision of domain or the signal function. So I am telling domain just to make it general, that it may not be always time, but it can also be a space in case of camera. Okay, so you are actually sampling the space, and so that domain would be the spatial positions or x y coordinates. So we can have the ADC output, the digital values can be represented in integer format, fixed point format, floating point format. So now, as I give some example, I want to multiply say 9.1 into 8.9. Now if I place it in microcontroller, it will actually give me 9 into 8, so 72. Okay, now let us add this 9.1 to 9.8.96. Okay, now if I take all these decimal values, that means 9.12 and 8.96, so I will get, and if we go for floating point computation, I will get the value as it is. Okay, now what is that? Okay, so what is that value? You can just compute 9.12 into this 8.96, and so 81.7152. Okay, 81.7152. Right, now instead I want to do it 9.1 into 8.9. So I am fixing, I am discarding this 2 and 6. Sorry, this is 9.1 into 8.9. And what is that value we get? We get 9.1 into 8.9, so 80.99. Okay. Right. So now what we can find, that integer computation is erroneous. Fixed point computation is little, means closer to the actual value. Now, if we use the fixed point format, we can consume less memory. Okay, so we can do it within, say, one register only, less memory. But for floating point computation, the same thing will require more, say 3 registers or so, depending upon the format you use, like say mantissa and exponent format. Okay, so the so that's how this fixed point format is optimal, in a sense that it consumes less memory, but it is closer to the actual value of the computation. Okay, and so instead of only using the integer format, we'll choose to compute it with fixed point format. Now one question still remains, that the fractional value we have, how to convert it into this fixed point format. Okay, so as I said, so this part is already explained, that how we can denote this, how we can find this q, the integer field qi. So alpha is 5 volt. Okay, 5. And so from there, with this relation, we can easily find this qi. Okay, then resolution, the number of fractional bit we want. So there are several methods, method 1 and method 2, for finding these qi. So once we get this qi, then we need to go for computations, that means arithmetic operations of these values. Okay, so arithmetic operations for multiplication, what we'll do, what we'll get actually. So if I multiply two numbers with qi1 qif format and qi2 and qf2 format, then we'll get at the output in the qi1 plus qi2. Okay, so this would be added. So qi1 plus this is actually this is w1, but the addition would be, integer field will be added together. Sorry, so this is this slides is talking about addition. So what we need to do, we need to align our numbers, align these two numbers, right? And so we need to convert this, which means we assumed here that qi2 is more than qi1, and so we need to align this qi1 to qi2. So how can I do that one? Okay, so let us assume that we have 91.35 and we want to add 5.12 to that, right? So what we do, we place some zero here, and so in our earlier notation it was 2.2 format in decimal. Okay, and this was actually 1.2 format, and now what we are doing, we are making this as 2.2 format, and then we are adding or subtracting. Now in case of binary, what we can do, so we have a register and say we have 1 dot to format. Now what we'll do, we'll shift this rightwards, and so we'll put a 0 here. We put the value, say this is A, put the value here, and this out of this 1 and 2 will be discarded. Okay, so say this is 5 points. Okay, let us erase it. So this was 5.12, and so this 5 will come here. Point will be shifted here, and only 1 will be kept and 2 will be outside, so discarded. Okay, so that would be our requirement. So for addition and subtraction. For multiplication and division, the QI product would be the multiplicand QI plus multiplier QI, and QF will be the same. For division, it will be the subtraction of that. Okay, so that means if I have, say, 5.12 into that 91.56, so I should get 3.4 format in decimal. Okay, that means this value, whatever value we will get here. So where it is required, hn into xn minus n, and then the summation addition is also required, these summation terms. Okay, so now we have the ADC and DAC. Okay, resolution is 2 to the power minus n. So what is fixed point format for ADC output and DAC input? That is one question, because we have also this xn term which will come out of this ADC. And so we have found that this QF is minus log 2 1 upon resolution. And if we say specify the resolution of the ADC is 2 to the power minus n bit ADC, 8 bit ADC, it will be 8, right? And so QF will be n, and since it is a n bit ADC, that means it is representing the data with n bits. So word length is n, and so the QI is n minus n, that means 0. So what does it mean? It means that the data which is coming out of the ADC, which is actually the signal xn, okay, so that is actually represented as a fraction. So q 0 dot, say, 8 format for 0808. Okay, now how this can happen, why this is becoming a fraction? So if you remember, so when we quantize the digital values, so we have divided the range, this 5 volt, into 256 levels for 8 bit. Okay, so each of these one is nothing but, say, this lowest bit LSB is nothing but 1 upon 256 of the 5 volt. Now 1 upon 256 is represented with the 0 0 0 0 0 0 0 1. Now what we are getting? We are getting this 1. So that means this part. And this value, so this 5 volt is implied. Right? And so definitely now if you see in that way, you can easily understand that this is indeed a fraction. Fraction of the reference voltage. Okay, so whatever xn you are getting, it is not the analog value, but the digital representation in fraction. Okay, so we get out of this given. Now say your hn you have represented in q dot q 3.5 format. Your xn is coming with q 0.8 format. Now if you are multiplying these two hn and xn, so what will be the output? Output would be q 3 plus 0 is 3 and 5 plus 8 is 13. That means it will consume 16 bits, right? Now how we can do it in our 8051? As we have said that we have multiplication mul AB. Now I want to ask how the output is getting saved from the student. I want a response.
Sir, higher nibble in B and lower nibble in A.
Very good. So not nibble.
Sir,
B is
byte.
a register. Yes. So we have lower byte in A and higher byte in B. So now what is content in the A is the fractional value, the rear end fractional value. So which means that after three values we'll have virtual point there, and after that whatever value is there, their fractional value, and the A contains the rear end fractional value, so we can discard it. So we can only take these B content and we'll come up with a 3.5 format again in the output. What we have lost some of the fractional values, and which possibly in our application can tolerate. We can tolerate it. Okay. And so after this mul AB, if we want to transfer it into port for DAC, so what we need to do? We need to move this content of B to A. Right? And then we can move it to say port 1 or port 2, whatever, wherever we are connecting our DAC, port 1 from this A. Right? So that we can utilize. So we'll take one example with the V reference, that this ADC. So we want to convert, sometimes if our computation is in the format of qi.qf, we need to convert it into q0.n for giving input to DAC, because DAC also takes the fractional value to regenerate the output at the DAC output end, analog signal. And if you remember, in the DAC also we have provided a V reference. Now this V reference can be different from ADC, but we generally keep it in as the same to replicate the same signal. Okay, so what we can do, so the V reference we first represent. So this is say 5 volt, so we represent the 5 volt first in this form. which is given, output of a computation. Okay, so we multiply this V reference with this QF factor. So say our QI is 3 and QF is 5. So that means what we'll do, we'll multiply this 5 into 2 to the power 5. Okay, so all these are in decimal. So if I get this value, so it is 32 into 5, 160 in decimal. If I convert it into hexadecimal, it will be A0 in hex. Okay, and then if I represent this in binary, we'll see this is 1010 for A, and then 0 0 0 0, and so now the 3 field, so this, since this is a 3 QI, so sorry, this 1 2 and 3, after that we have a virtual dot point, binary point now, and now you see this is 5, this is 100, I mean 0 0, all zeros. So this 5 volt is represented in a with a fixed point format as A0. Okay, then what we do, multiply the Q0.n version of ADC output. So ADC, from ADC we are getting some value, so we are multiplying with these, so we'll get the multiplied output will be Qi.n plus QF, and then what we'll be doing, so sorry, this is actually from 0.n to 3.5 we want to convert it, and then if we divide it by 2 to the power n, I will get the output. Which output? The input signal, which was available in 0.n format. Now we want to multiply it, means represent it in 3.5 format. So this ADC will be, if we divide it by n, so definitely this term will be subtracted, right? And so we'll get an output with qi.qf format. So if it is required for the computation, input for the computation, whatever I have told, I have given with numerical expression, that this is q 3.5, but now here we have this one somehow. So this is not, I think, correct one. 160 is A0, so 101 and 000. Okay, all zeros. Then say we multiply this 0.n version of 2.5 volt. So the 2.5 volt will be like this. Okay, so this is divided by 2. If all ones, it is 5, and then divided by 2 means right shift by 1 unit, and so this is 2.5 volt. So if you multiply these two, okay, so if you take this, it is 4.99 as if, right? So this can also, due to say some imprecision, it is 4 point something 9. So now if you multiply it, right, so you will get this in 3.13 format. So 3 values from here you have to take, and then you need to place your decimal point here. Now you are finding this is 0 1 0, which means 2, and then if you add all these component with 2 to the power minus 1, then 2 to the power minus 2 as the position. Okay, and for whatever you are getting 1, that should be added, you will convert to 2 to the 2.5. Okay, but it is available in the 3.13 format. So what you are doing, you are dividing it by 8, and so that means 1 2 3 4 5 6 7 8. So this part is truncated, so it will be closer to 2.5 but not exactly 2.5. Okay, so this is the representation of the input signal which was available in 0.n, we can convert it into 3.5 if required for the computation. So the fixed point computation system is something like this, that we get input from the ADC 0.n format and then convert it into qi.qf format. Then we can use the fixed point mathematical rules, arithmetic operation rules. We get the output in qi.qf format, and then we need to convert it again to 0.n format. And this is just the reverse operation of this. So what is that reverse operation? We first multiply it by 2 to the power 8. Okay, that means we'll append. So we had this output in 8-bit format, we will append the some zeros here. Okay, so this will be in A, this will be in B. So that means we will be using left shift to multiply 8 times left shift to multiply by 2 to the power 8, right? So once this is done, then what we need to do? We need to divide it by the V reference represented in qi.qf. Okay, so we'll be dividing it here. We'll get this value in q dot 0. So first we multiply, then we represent the V reference in the format qi.qf, then divide that representation 16-bit number by this representation 8-bit number and get the DAC input value. Just reverse operation, we can do it. Okay, now we want to implement this direct form 1 in this form. We already known. Direct form 2, there are different structure of filter. Now what is the advantage and disadvantages of that? So basically that advantage and disadvantages is prominent when we have this number of multiplier and the adder available with us. But since we do not have number of multipliers and adders, but we have only single LU, so that advantage will not be very prominent in 8051. Okay, so because we have to add all these multiplier timing and adder timing. But when we have number of multipliers with us, we can get this advantage that our computation time would be reduced to only this TM plus this TA instead of the earlier version. So this TM plus this TA plus this TA, so 2TA. So that is, so what is the implication of that? So implication is this unit, this structure will be slower than this structure. Okay, and so the frequency range input signal data, so that will have a higher frequency, cutoff frequency here, FC, so FC1, and this say FC2, the maximum range. So FC2 will be higher than FC1. That means we can go a little bit higher frequency range with this structure, but that is only when number of multiplier and the adder are available. Okay, so what we can do, that we have, so direct form 1 will be doing this way. Okay, we can implement the IIR filter. Now this convolution operation is to be implemented here. So fixed point mathematics is related to this model, right? Okay, earlier we had to compute this one. Now as I said, that one of the issue is stability issue. So I will suggest you to go through the proof of this, that why we should use a second order cascaded unit. So for general one, Hz can be represented as this, and you can see that we have some number of poles here, which is say closer to unit circle or so, or they are very close to each other, right? And we can represent that AK, which is the representation in the 8-bit format, which can be expressed as a infinite resolution plus some error. Okay, and similar is true for the poles and these zeros, right? And now what happens that, say as I said, that our value is 5.12, and because of the our fixed point representation, these two get cancelled, and there was another pole at 5.13 or say 4, but because of this process, this 4 is also getting cancelled, and you can see that two values are appeared to be same because of this imprecision. Okay, and so what will affect here, the two poles will fall in the same location, so definitely it is going to change the frequency response. Okay, now if you see that this dz or this pole, okay, so this pole expression can be so this denominator expression can also be represented in terms of factors with poles. Okay, and then if we differentiate this pole with respect to this del ak, that means change in the coefficient, how the pole locations are getting affected. So del pi by del ak. So that is the meaning of this. We see that we have a term pi minus pl, that means the distance between the different poles in the denominator. What it means that if this distance is very small, say 0, that means the sensitivity is very high. That means a small changes in del ak will affect these changes in the pole locations drastically. Okay, so what is needed? We need to ensure that this distance must be higher value than zeros. Okay, so that can only be obtained when we have divided it into second order filter, because in case of second order filter, the poles will come in a complex conjugate manner, and therefore it will never be close to each other, so this distance will always be ensured to be having higher value, right? And so each of these filter is stable, and so in cascade the overall system will be stable. So this is the concept we employ here. So locations of poles are highly sensitive when they are least apart. Second order system ensures higher distance between these poles, and so the sensitivity will be less. Sensitivity will be there, but it will be less. So we'll go with the second order system. And that's why now it is clear to you that why this MATLAB FPA tool is providing that values, right, in with second order cascades. So when we go for, so that also be we will affect the FIR frequency response, right? So that's why it is always better to convert this higher order filter into cascaded second order filter. And so instead of implementing the Hz as a whole, we'll divide it into H1Z, H2Z, Hn, which are the factor of this. and then we'll employ the second order filter for each of them, right? And then we'll do that operation. Now for streaming data, we'll give some idea for coding, that when it comes from the analog to digital through this ADC, we get the XN. XN is available at the port. Okay. Now at the first instance, we get this XN. Okay, and we assume that in RAM location these values are there. So at the beginning these values will be 0. But afterwards, this xn will be moved to xn minus 1 location. Xn minus 1 location will be moved to xn minus 2 location. So the operation would be, first you move this xn minus 1 content to xn minus 2. Then you move the xn content to xn minus 1. Right? And then new xn will come appear here. Now since we have only single ALU, so this is our ALU. So single ALU, so we have to do this operation sequentially, one at a time, right? So first we can do whatever is appeared here, this xn, we move it to accumulator. We bring H0 into the B and we use the mul AB operation, right? We save this result. So this result should be saved to say mul n. So you can see that this is the 0th activity and this is also 0th activity in with respect to this register. So that means the result will be saved into this register. Okay, when this xn into h0, xn into h0 is saved in mln. Then on next one, this xn minus 1 will be fetched, this h1 will be fetched, and then multiplication. Then that result will also be placed mln minus 1. Okay, so that is at the nth. N minus means this value will be stored at first activity, 0 after that next activity. Then this xn minus 2 will be fetched, and then this h2 is fetched and multiplied. And now what we have to do, we have to invoke the addition operation. So what we need now, this third activity is this. Now the result will be available in the accumulator of this multiplication of xn minus 2 into h2, so that will be available in accumulator. So we'll face this means output of the first one to there and add this. So this third activity is addition between this last multiplication and this first multiplication. Then we can go for next addition, that the result again will be at accumulator, and then we can use this mln minus 1 and add it, and finally we'll get the result in B, and then that should be moved to accumulator. So because we learned that with fixed point representation our result will be 16-bit result, and we'll just move it to this accumulator from B, because B is the MSB, which is the significant one. So this is giving you some way of writing your code, how you can write your code. So you have to do it by yourself. And this time, since you are separated from, so you cannot have a group also. But when ever you are working on the hardware after coming back, so that time you can make a group of 2 people or maximum 3 people, and then you can implement it on the hardware. But till that time you work with the simulator. Now apart from that, we can have also a visual representation of the time register map, which I will call it as this. Then we have this ADC, which will take some time to convert So the SC, the start conversion signal, is invoked at T1, say. So at T1 plus conversion, so at that instant we'll get the first sample, this xn, and then we'll do this multiplication and addition operation, which I have just now explained. So we have 3 multiplication, we have multiplied and then means place those content here, and then we are adding. After adding whatever we are getting, passing it to DA. DA may take some time to uh, provide the output, and after that your SC should start, or we can neglect this time DA and SC can be here. But what is pointed here is that for each sample, what we are taking 1, 2, 3, 4, 5, 6, 7. So 7 registers from the RAM location. Okay, and so the 7 register can do, and then this T conversion. So this T conversion, then this, say this operation takes TF. Okay, and so what we'll get, the TS. So you should not do this. This is sum. This will be actually T1 plus this T conversion plus this filter now introduced, so TF, and plus you will have some saving. So you will be executing some instruction to save this content, so that I am clubbing into that TS. So TS is for saving, so TSV rather. Okay, and that will constitute this sampling time, the TS. Now in this case, this T conversion can be, so basically this won't be there, right? So that is the starting instance, so I can move this T1. So this will develop this, constitute this TS. So this can be 0 compared to TF. This can also be 0 compared to TF. But if it is not, then you have to consider all these. Okay. And so this TF is almost the major contributing term in the sampling period. And so your Fs would be the 1 by this computation time. Now, how this TF is dependent to order of the filter? So as we have said, for second order, or in general, M into Tm plus M minus 1 into Ta, right? So it is dependent on the M, it is dependent on the multiplication instruction. In case of say 8051, it is 24 clock cycle. Okay, then Ta, the addition instruction, and then it will be multiplied with this. So if M is higher, then it will be higher, and so Fs will be less, and so your input frequency range will be less. Okay, so with this this discussion, what we have found, that to implement a digital filter on 8051, inside it, what we can do, we can represent the signals and the coefficients in fixed point format, and so whatever coefficients value we get from MATLAB filter design tool, those are say fractional value, and now you want to convert it into say to 0.8 format. So if you want to convert it into 0.8 format, so what you have to do, the coefficient value, that ak say should be multiplied by 2 to the power 8. So if you do so, it will convert it into that q 0.8 format. Now your computation would be easy, okay, because the multiplier would be 0.16 format, and so you will always get everything in frequent means fraction. So at the output end, the DAC input, so that will also be 0.8 format, so you do not need to convert it into within the fixed point domain, okay. But when you go for IIR representation, you may some coefficients are integers, like you have seen 1 to 1 in the numerator. Okay. So you need to find the maximum value of that coefficient, and you need to find the QI. Okay. And then obviously QI for this case is 2. And so your format should be QI dot QF, that should be in 2.6 format in our case, okay. And so if that is the case, then your fixed point computation will produce result with 2.14 format, and from there you will get 2.6 format just by truncating it, okay. So once you get that 2.6 format, so now at the input of this DAC, what you have to do, you have to convert this 2.6 format into 0.8 format. How can you do that? We have already explained it by that process. So that process should be invoked. So it is the multiplication with, so that means you add some zeros, then you divide it by the V reference. So you need to know the V reference in 2.6 format. Okay. Now if V reference is 5 volt, it is 3.5 format, right? So how can you do that then? This is very easy. You need to make, so this 2.6 format can be converted to 3.5 format just by right shift. Okay. And then you use the 3.5 format representation of the reference voltage, and then you divide it, you will get the 0.8 format, and then you place this value to the DAC. So this part will also come into the picture apart from this TF, right? After TF, so if we refine that, so it will be TF plus then, so T field plus T fixed point computation. Okay, so this is just fixed point conversion, okay, FXC. So that will come into picture, and that may be significant, and accordingly your TS will be formed, right? So we have taken care the computational accuracy with the help of fixed point computation, the usage, stability issue with the second order cascaded structure, right? And the timing issue, actually we cannot means change it as such. What we can instead, what we can do, we can specify the maximum input range that the system will work for. And so because we have this FIR and IR structure, and with this structure also, since the outputs are, you know, are also taken into account in case of IR, okay, so it will be a little bit slower than the FIR with the same order. because number of multiplications and additions are getting increased, and therefore the IR implementation of same order will have less frequency range, input frequency range compared to FIR1. Right. So, any questions you have so far regarding implementation? So we have handled all these issues: real-time issues, the computational accuracy issues, then stability issues. And one point here I need to highlight, that this cascade. Now, what will be the sequence of cascade? As we are doing H1Z, H2Z, HNZ, because this cascading is commutative in nature. So I can place this H2Z earlier and I can place H1Z later. But what should be the actual sequence or proper sequence? So you go through that book again, where it is telling that the sequence will affect the noise enhancement at the output. So we need to have a certain sequence with, I think, decreasing order of the gain of the second order systems or so. And so that means you have to first place the maximum suppression of the noise, and then gradually you go with the means less suppressions of the noise. So that way you have to place your sequence so that the noise which is available at the input will not be enhanced at the output. Instead, it will be suppressed at the output. So the second order cascade with a proper sequence. That is the philosophy of our work. And then fixed point computation. So, and we can everything we can correlate with our theoretical understanding, which we learn from different domain, and then we can work with this 8051. Means with the instruction sets which you have already learned. So if you have any question, you just raise and we will close today.
Sir, those
Yeah.
who don't have MATLAB, what they will do to find the coefficients, and as MATLAB is cannot be activated, can
Why
download
cannot
but
be?
can.
It can be
Sir,
activated if it is from.
the institute license is deactivated.
No, no,
So
no. Institute license is renewed. Okay.
okay, sir.
This time institute license is renewed, and what I showed to you, this MATLAB is with institute license only. So I think last Monday onwards it is renewed.
Okay, sir. I will get the details soon.
Yes. So that is renewed. You can utilize, and if you cannot, then you need to know whatever I have taught you. So and then you can code it. Okay. So let me show you some coding. So this was actually done before the MATLAB license was renewed. So that was done with Scilab, but this similar code can be generated in MATLAB also. So Scilab is open source, so anybody can utilize that. And so for say FIR design, okay, so I will show you in between. If you have any further questions, you can uh, generate. So you can see this one. Yeah. So this was a code written by me where this fs is 3000, then fc is 300, then m is 101, and I have used this expression. So you have to do it using your pen and paper. Okay, so what design with Windows. Okay, so this expression. Okay, so h omega. So how did I get this? So I have placed some m second order or so. I get the desired one, and then I have done this inverse Fourier transform, get this hn. Once we get this, we can utilize this expression to find the hn itself. Okay, so hn can be generated from this. Then window function is defined. Then we can so this is for comparison of rectangular window and the Hamming window. Because of that, I have used these two different variable. So once this is done, then absolute value, and then I have normalized it, and then we are plotting with respect to the analog frequency, which is actually, you can see from here that fc would be fc by fs, and the digital range is 0.5 to minus 0.5 to 0.5. And so if I multiply f with the fs, we'll get the analog frequency range. Okay, and so if I plot it and run it, so we'll get that value. So the frequency response can be observed here, and by giving this hn, sorry, I think this is hn, right? So you get this coefficient here, right? So this way, this is the alternative way, so which will take a little bit time, but we can do, right? And since we have now our MATLAB renewed, so we can use the FDA tool. Any further question?
No, sir.
Okay, so I think you all learned it. So now what you have to do, the work mode. Work mode is that I will provide you tentatively the lab sessions you need to work, which task in which lab, which day basically. And then after completion of that particular task, so we can interact with each other. Okay, so that whatever problem you are facing, and then means a solutions, a guidelines can be provided to you. Will it be useful for you?
Yes, sir.
Yes, so that would be useful. So what will be there, that every week will be online in the same time, but not always will be interacting, because you have to work yourself first. Once your work is over or you are facing some problem, only for that we'll go for a guideline, and that should be after a consolidated, means all of you are facing a similar problem. If someone is facing a problem and someone has already solved that problem, so that you can do with your interaction between yourself. Okay, so first you try to interact with yourself, and then whenever means all are fail to solve that problem, then you interact with me. That would be the best option. But we'll do means this uh, Tuesday 8 to 11, that time slot will be used or consumed for the lab session only. So don't means what we can say, don't deceive yourself, rather, not should not be to teachers. Don't deceive yourself, put your effort during this time and then learn this subject. Is that okay?
Yes, sir.
So whatever video is recorded today, so you can distribute it to your other group so that they will also know that what is to be done